particular what I see is that the Radon transform of the summation k from 1 to n, L from 1 to n, summation of a k times B L times the second derivative of f with respect to these variables. I see that each derivative with respect to each variable is going to bring in a respective direction cosine. So, let me just replace this double sum with this corresponding direction cosine, and what I get is the following. So, I get that in this general case my right hand side is a dot with u, right. So, what I have is that this is a dot with u. So, that is the most general derivative. We see that we are summing up from k 1 to n. So, we are taking all possible derivatives from 1 to n. So, that is bringing in the corresponding direction cosines, and then times b with u times the second derivative. This is the second derivative of f in the physical plane, and then the Radon transform will be equivalent to the second derivative of the Radon transform of the function with respect to p square. Okay. So, this is the general, this is the most general result of the second derivative of the Radon, well, the general result on the second derivative application of Radon transform on the second derivative of the function. Okay. So, then let me just look at a specific case of this part D. So, in particular what I have is that suppose I have that I need to evaluate the Radon transform of the second derivative of f with respect to x k and x l. So, let us say my a and b, these coefficients are all 1, right. So, in particular if my a k and my b l, these are all 1, right. Well, a k and b l are such that a k b l, well, in such that my a k, well, my a k and my b l, they are all 1, of course. Then my Radon transform of this corresponding second derivative will be the corresponding direction cosines u k times u l times the second derivative of the Radon transform of f with respect to p. And I see that this is nothing but, if these are the direction cosines, this will be nothing but the delta function of k with respect to l, right. So, since this being the direction cosines. So, well, so then let me just state this result in a more specific situation, that is, if I have that the product of a k b l is equal to the delta function. So, if I have that a k b l is the delta function, then in that case my Radon transform of the Laplacian of f, notice that if a k times b l in this summation can be replaced by the delta function, then the Radon transform changes to this Laplacian, the corresponding Laplacian, and then that will be equal to u k times u l. So, u k and u l is nothing but the quantities of, well, replacing u k and u l by its magnitude times its direction, I get that this is also equal to mod u square. This is for n dimensions. This is the result in n dimensions. So, mod u square del square, the second derivative of the Radon transform with respect to the variable p. Now, I know that this is a unit vector. So, since this is a unit vector, the magnitude is 1, and I get that the Radon transform of the Laplacian of f is the derivative of f with respect to p, the second derivative. Notice, so this last result is particularly important. Notice that I am changing, if I were to work on a problem which is n dimensional. So, in that case I have to evaluate the Laplacian in for n dimensional case. All I need to do is change it into a 1D problem by taking the appropriate Redon transform, and this Laplacian in n dimension changes to the second derivative in 1 dimension after taking the Redon transform. So, an n dimensional problem is changed to a 1 dimensional problem. Okay. So, let's continue our discussion on Redon transform, the derivatives. Okay. So, I have some more results. So, let me just continue my topic of discussion. So, before I move on to describe more properties on derivatives, notice the following. Note the following property of the delta function. Note that the delta function of delta of x minus y, if I were to differentiate with respect to x, that is also equal to negative the derivative of the delta function with respect to the other variable. Okay. So, that follows from the definition of the delta function in the generalized sense. Okay. So, if I were to make the following substitution, replacing y by b of y, I see that my delta function, the derivative of this delta function, delta of x minus b y, derivative with respect to this new variable b y, this is also equal to, of course, 1 by b times the derivative of the delta function, derivative of the derivative of the delta function x minus b y, right. So, this is also equal to 1 by b times the derivative of the delta function x minus b y. So, I see that this is also, let us see what happens. I see that 1 by b times the derivative of the delta function delta of x minus b y, this is using the property listed above, this is also equal to the negative of the derivative with respect to x of delta of x minus b y. So, if I have a scalar multiplication with one of the variables, so this property follows right away from my first case. Now, for an n dimensional case, what I have is, I have to find the derivative of the delta function, with respect to, I can generalize my previous results for the n dimensional case, that is the derivative of the delta function with the jth component. This is also equal to the derivative of the delta function, with respect to the jth component of x with a minus sign. So, the minus sign can be flipped back and forth. Okay. So, the derivative with respect to jth matches with the derivative with respect to the jth of the x and the y components. Okay. So, then so these are some of the useful properties that I am going to be using in my following results. So, there is one more property which says that the derivative of the delta function in the hyperplane. So, now I am going to the hyperplane case. So, p minus chi times x. So, that is the derivative with respect to the hyperplane. This is also equal to negative the derivative with respect to the delta function of p minus chi dot x. I see that this is also equal to the derivative of f. So, notice that this above property follows right away from my derivative property of the delta function. Okay. So, which means that if I were to take this new property says that if I were to take the derivative of this Redon transform with respect to the direction cosine uk, that equals to the derivative of f with respect to zeta k, and that is evaluated at zeta is equal to u. Okay. So, what I have done is, in order to take the derivative of the Redon transform with respect to individual direction cosines, all I do is I take the derivative of the Redon transform for the arbitrary variable z chi and take the limit, evaluate this limit at chi equal to the direction cosine. Okay. So, this particular expression, this particular equality serves as the definition of the derivative of the Redon transform with respect to the direction cosines. Okay. So, notice that this particular derivative can be written as an integral from negative infinity. So, I am now going to replace my definition of the Redon transform here. So, my Redon transform is the integral of f of x times the derivative of zeta k delta of p minus zeta dot x, okay, dx. Okay. So, I have just used the definition of the Redon transform, that is the projection of the function on the hyperplane p equal to zeta dot x, and I have now taken the derivative inside the integral. So, this definition can be replaced by this definition by taking the derivative inside the integral, and I see that when I evaluate this at zeta equal to the direction cosine. So, when this integral is evaluated at this value of the angle, I see that this is also equal to, now I am going to use the property of the delta function, namely the property says that if I were to differentiate with respect to the second variable, that is negative times the differentiation with respect to the first variable of the delta function. So, this is also equal to negative del p times the integral with respect to the first variable. Well, so that becomes x k, that is the kth component of f of x times delta function evaluated at this hyperplane x dot u. Okay. So, again the integral is with respect to x. Okay. So, after using, so we see that if I were to evaluate the derivative of the Redon transform at a particular value of the direction cosine with respect to the angle, all I have to do is find the corresponding derivative with respect to p of this particular integral. Okay. So, the result that I have got is the following. So, let me call this as 1. So, 1 says that if I were to evaluate the Redon transform, the derivative of the Redon transform with respect to the direction cosine, this is also equal to the derivative with respect to the Redon transform of the function of f of x with respect to zeta k. Okay. So, zeta k evaluated at zeta equal to u. Now, I see that this is from the definition above is nothing but the derivative of negative the derivative of the Redon transform with respect to the other variable p, that follows right away from these steps that I have outlined in 1. So, I can see that this is the, so that gives us the relation for the other derivatives that we will be using. Okay. So, let me just give the more general result. So, more general result, the general case is that if I were to find the derivative of the Redon transform of f with respect to any direction cosine, and let us say that with respect to any scalar I take the dot product. So, suppose if the scalar is I hat, then I am taking the derivative with respect to the direction cosine along x, along the axis x. So, the specific cases follow. So, this general result tells me that this is also equal to the negative of the derivative with respect to the variable p of the Redon transform of a dot x of f of x, okay, of this Redon transform. Okay. So, we see that a dot x, if x is I hat, I get the corresponding variables here in the respective directions, right. So, if x a is I hat, here in the left hand side I see that the derivative is with respect to x, and on the right hand side this dot product is reduced to the variable along the x direction. Okay. So, the specific cases follow from this general result. Okay. So, then let me look at higher order derivatives. Let me look at the higher order derivatives. I see that to find the second derivative of f hat with respect to u l and u k. So, that becomes negative minus 1 square, the derivative of the Redon transform with respect to the following function x l x k f of x dx. So, I have just generalized this following result with respect to the second derivative that I have found. So, let me continue writing for higher derivatives. I see that this is also equal to, let me see what is the third derivative, this is del u l del square u k. I see that this is negative minus 1 cube. I am just generalizing this result for second derivative, third derivative and so on. So, this is del square p cube, the Redon transform of x l x k square f of x, and let me just now write down the more general case. So, let me write down the general case for the second derivative here. So, the general case is del square f hat del u k del u l minus, well, times a k b l k comma l from 1 to n. Let me just generalize this result. This is also equal to the Redon transform of with respect to p of the following function. We see that this is, notice that these are the corresponding direction cosines. So, I get the corresponding expression in this right hand side. This is a dot x b dot y f of x bar. Okay. So, that is the second derivative. Now, if we were to look at the general case, the general derivative of the general n dimensional function, the general case now. So, the most general case is the k plus lth derivative, the k plus lth derivative. Let me say that this is u 1 to the power k, and well, not u 1 to the power k, but the kth derivative with respect to u 1 and the lth derivative with respect to u 2 of the Redon transform of p comma u. This is, well, each derivative is going to bring out a minus 1 sign. So, I get that this is minus 1 to the power k plus l of the Redon transform of x to the power k x to the power l f of x. Okay. So, that completes the basic outlining of the properties of the derivatives of the Redon transform. So, that is all what I had to say about the derivatives of the Redon transform. Well, there is one more result that I would like to highlight, that is the integral, the result on the integral of Redon transform. So, in general, let me just state the result. So, the result says, this is the result with respect to the integration of Redon transform, the integration of the Redon transform. I see the following. So, this is with respect to P. I see that the integral from minus infinity to infinity of the Radon transform with respect to the variable P is given by the following integral in the physical plane. Okay. So, I see that the Radon transform integral can be rewritten to a new integral in the physical plane. So, the integral in the physical plane is equivalent to the integral in the transformed plane. Okay. So, let us now look at an example. Okay. So, let us, using all these properties that I have outlined, let us see how to find the Radon transform of some well known function. Okay. So, the example is I have to find the Radon transform of the nth order Hermite polynomial. So, what are Hermite polynomials? So, Hermite polynomials of order n. Let me call this as Hn of x. Okay. So, I define my Hermite polynomials as follows. My Hermite polynomials Hn of x is defined by this relation e to the power negative x square Hn of x time is equal to minus 1 to the power n times the nth derivative with respect to n of e to the power negative x square. Okay. So, I see the following, see the fact that now, so let me call this as 1. So, according to my definition 1, my definition 1 gives me the definition of the Hermite polynomial. So, if I were to find the Hermite polynomial of order n, I need to differentiate the right hand side with respect to n, well, with respect to x n times. Okay. So, I see that this is also equal to, well, I have to show the following fact. I have to find the Radon transform of the Hermite polynomial of order L and the Radon times the Hermite polynomial of order y e to the power minus x square plus y square. Okay. And I have to find, well, I have to show that this is also equal to square root of pi times the corresponding direction cosines cos phi of L times sin phi of k times e to the power negative p square times the Hermite polynomial L plus k of p. Okay. So, let me start the solution by let us using this expression 1 for the 2D case. Okay. So, using my expression 1, let us see what happens. So, for a 2D case. Okay. So, for a 2D case. So, what I mean by that is, notice what happens to this following product e to the power minus x square Hn of x times e to the power minus y square Hn of y. Okay. So, what I have is, I have to find the Hermite, the product of these two Hermite functions. I see that this is also equal to e to the power minus x square plus y square of times the Hermite polynomial. Let me change the order. So, this is the Hermite polynomial of order k. Well, I need L of x. So, this will be Hermite polynomial of order L and order k with respect to y. Okay. So, I get h L of x times h k of y, that is, now I am going to use the definition of the Hermite polynomial given in 1. So, h L of x e to the power minus x square h L of x, this is also equal to minus 1 to the power this time L, and the kth order Hermite polynomial will also bring in minus 1 to the power k. So, I get minus 1 to the power k plus L, and this is also equal to, notice that this is the nth order derivative for the Hermite polynomial of order n. So, I get the derivative of the order k plus L. Okay. Well, the derivative with respect to x of order k and the derivative, well, let me rewrite the left hand side for better clarity. So, the left hand side is the right hand side is minus 1 to the power k plus L times the derivative with respect to L, that is the kth order derivative, times the derivative with respect to y of the lth order derivative. Okay. So, I have L with respect to x, so that will be an L, and I have k with respect to y, so that will be a k here. Okay. So, then of e to the power minus x square times e to the power minus y square. So, I have e to the power minus x square plus y square. Okay. So, notice, let us see what happens. Now, I am going to take the Radon transform of the left hand side. So, let me say that this is, well, let me look at this expression, let me call that this is equal to 1. Okay. Well, I have already defined it 1. So, let me call it as 2. So, now apply my Radon transform, to 2. I see the following. I see that my left hand side of the expression 2 becomes r of e to the power minus x square plus y square times the Radon transform H L of x times the Radon transform H k of y. Okay. So, see that this is also equal to, now I am going to take the Radon transform here on the right hand side, this will be equal to minus 1 to the power k plus L times, now notice that I am differentiating with respect to x and y. So, each derivative of x is going to bring in a direction cosine with respect to x, that is cos of phi, and each derivative of y is going to bring in a direction cosine with respect to y, that is sine of phi. So, hence I get cos of phi to the power L times sine of phi to the power k, and then the Radon transform of this quantity has already been evaluated in one of my previous examples, and that is, so let me write this, that I have to evaluate the Radon transform of this quantity denoted here by star. So, let me call this as r of e to the power negative x square plus y square. Okay. So, that has already been evaluated in my previous example. So, what I see is the following. I see that the Radon transform, that is my left hand side, the Radon transform of e to the power minus x square plus y square of H L of x, that is the product of the two Hermite polynomials h k of y, this is negative 1 to the power k plus L times cos phi of k sin phi of L times the Radon transform of the quantity e to the power minus x square plus y square, and I write the result for that right away by evaluating the Radon transform, that is square root pi e to the power minus p square. Okay. So, this means that I have the following result. Well, what I have shown here is that let me just rewrite this right hand side. We see that this is also square root of pi cos, we see that this is cos phi. So, I am rewriting this right hand side now, sin phi to the power L, and what I am left with is the, well, notice this factor e to the power minus p square times minus 1 to the power k plus L. So, this one will be nothing but e to the power, well, using my expression 1, this is also equal to e to the power negative p square times the Hermite polynomial of order k plus L of evaluated at the expression p. So, I get this result using my definition of using my definition of Hermite polynomial given in 1 in this problem. So then the result follows. The result follows that this is so the result follows. Okay. So, what I have is that the Hermite polynomial, the product of the Hermite polynomial HL of x, HK of y, e to the power minus x square plus y square, and that is also equal to, well, let me rewrite this right hand side. This is square root pi cos phi to the power k. These are the corresponding direction cosines with respect to x and y times e to the power minus p square, the Hermite polynomial of of order L plus k of p, and that is what my result that I had to show. Okay, so then I am going to end my discussion on Redon transform for this lecture here, and in my next lecture I am going to continue describing more results on Redon transform, and specifically I am going to solve some application problems in this particular case. And later on in my next lecture after that, I am going to shift my focus into another calculus known as the fractional calculus. In fractional calculus, we will be using some very interesting properties of derivatives and integrals and evaluate those integrals using all these transforms that we have developed. And towards the later half of this course, I am also going to introduce the very famous wavelet transform. Thank you for listening today. Thank you very much.